Okay, today we're talking about continuity and one-sided limits. Okay, right here in the middle, this homework, we can cross that out. All right, for a function to be continuous, it has to be unbroken. This means there are no holes, jumps, or gaps. In other words, you must be able to draw the graph of the function without picking up your pencil. Here's 3 examples of functions that are not continuous. Not continuous. Okay, f of c is not defined, so you have a hole. The limit does not exist, you have an asymptote. Or a hole, or a jump, okay? You could have a jump or an asymptote. And then the limit doesn't equal the value of c. That's one of those graphs where you have a line with a hole in it, and the function is defined up here instead. Okay, so the limit is equal to, let's say this is 2, and this is equal to 6. They're not equal. All right, the definition of continuity. This is a big deal, all right? Big deal. Definition. Pay attention. Note it. A function is continuous at c if the following 3 conditions are met. I'm going to change the way these are written. The first one is that f of c is defined. The second one is the limit as x goes to c of f of x exists. And number 3, the limit as x goes to c of f of x is equal to f of c. All 3 conditions must be met in order for it to be continuous. Okay? Then we're going to go down here and they talk about an open interval, because on the next page we talk about closed intervals. So open interval, function is continuous on an open interval AB, from A to B, if it is continuous at every point in the interval, okay, each point. A function is continuous on the entire number line from negative infinity to infinity, is everywhere continuous. I don't know if I've ever used that word, okay? I don't know if anybody ever talks about that. But it's on the paper, so we'll talk about it. All right, examples. There's a couple corrections to make. First, cross out the +1. This should be a piecewise function like this, and this is when x is not equal to 1, and it's 4 when x equals 1. I've got to retype these notes, and I'll fix that. Okay, and this one I'm going to change also to x squared minus 1, x minus 1. So put that in your notes. Fix it. All right. Now, if I factor this, you get x minus 1, x plus 1. Here's x minus 1. They cross out. You've got a line with a hole in it. There's a hole right here. Okay, so that's an example where f of c doesn't exist, is not defined. All right, this graph, it's a piecewise function. We have a line, starts at 1, goes this way. This is, and that's a closed circle. This is an open circle, it goes this way. It's a function, okay? But the limit doesn't equal f of c. So that's an example of the third one. Or, sorry, the second one. The limit doesn't exist in the first place. The limit can't equal a value if you have no limit, okay? So this is no limit, no limit, no f of c. And this one is the same as the first problem, only I redefined the function. So it comes up here and has a hole, but I defined it to equal 4. So now the limit exists. The limit here is, you got a limit, but here's the f of c value, and they're not equal. So that's an example of all 3 of those conditions. Okay? If a function is not continuous, then we call it discontinuous. Discontinuities come in 2 flavors, removable and non-removable. Removable discontinuities can be made continuous by appropriately defining f of c. This is an example. All right, non-removable mean you have a jump or an asymptote. There's no easy way to fix that. Removable ones have a hole, and you can just define it. So like example 3, I defined the whole to have a value. So it makes it, so if I wanted to do that, instead of defining the whole, instead of saying when x is equal to 1, I would have said it was 2, and that would have filled in the whole. Okay? You define it and fill the hole in. Make sense? That was kind of sloppy, but figure it out. All right, one-sided limits. That was yesterday's lesson. In order to determine whether an interval is continuous on a closed interval, here's that word, closed. I did it again, guys. How do I get rid of that? Ugh. Closed interval. We must know whether the function has a one-sided limit on the left and right of the interval. A limit from the right side, or the right side limit, means x approaches c from values greater than c. Left side comes in from the left. We did that yesterday, right? This is the limit as x approaches c from the right. This is the limit as x approaches c from the left. Okay, one-sided limits can occur when normal limits do not. That's kind of a big point. Let's highlight that. That was a turn the page. Okay, one-sided limits can occur when normal limits do not. This leads to the definition of the existence of a limit. Let f be a function, and let c and l be real numbers. The limit of f of x as x approaches c is L if and only if the, the limit as x goes to c from the left equals L, and the limit as x approaches c from the right equals L. So the right-hand limit and left-hand limit have to be the same in order for a limit to exist. Okay, we can use this idea and extend the definition of continuity on an open interval to a definition of continuity on a closed interval. Okay, so we're going to have that closed interval. A function is continuous on the closed interval AB if it's continuous on the open interval. I didn't pick up my pencil when I drew it. These are closed points, okay? The limit at A, the right-hand limit at A equals f of A, and the left-hand limit at B equals B. Okay, so I'm coming in this way. The limit has to equal that value. Come in this way, the limit equals that value. Makes sense. The problem is that there's no limits on the outside, so we have to talk about one-sided limits. Okay, the function f is continuous from the right and continuous from the left at AB. Okay, so we want to determine, here's an example. We want to determine if f of x equals the square root of 1 minus x squared is continuous on the interval from -1 to 1. Well, I'm going to rewrite that problem as y equals the square root of 1 minus x squared. I'm going to square both sides, add x squared to the other side. Anybody know what that graph is? Yep, it's a circle with a radius of 1. So if I'm going to graph it, it starts at the origin, goes like this. This is -1 and 1. It's only the top half because we have a positive root. Okay? It's a continuous function. Yep. Don't have to pick up my pencil. Now I have to check my limits. Is the limit as x goes to -1 from the right equal to f of -1? Well, this is equal to 0. And if I plug -1 in here, you get the square root of 0, which is 0. So that's true. And then I have to check if the limit as x approaches +1 from the left is equal to f of 1. Well, again, it's equal to 0 and 0. So yes, it's continuous on the closed interval. Note the brackets make it closed. And there's a difference between closed interval and open intervals. Okay, last thing in today's lesson, it says this: f is continuous on a closed interval, a to b, and k is any number between f of a and f of b. There's at least one value in c in a and b such that f of c is equal to k. This is the intermediate value theorem. It's used to show that a zero exists for a function in AB. For example, if f is continuous and f of 2 equals 6 and f of 4 equals negative 2, we can show that a zero for the function is in between 2 and 4. You've done that in algebra 2. You said, well, if you have a positive and a negative, it's got to cross the x-axis somewhere so it equals 0. Okay? Now we've just got a theorem to prove it. But let's talk about this theorem. Okay? Here's A, here's B. Let's make this f of A, and this is f of B, and here goes my function, okay? What the theorem says is that there's a k between that, and this is important. If you're given a y value between the y's, it's not an x between the x, they're giving you a y between the y's, then there has to be a c value in between A and B. But that's important. You can't do it in reverse. It does not work in reverse. If they tell you C is in between A and B, K might not be. Okay, you might have an answer up here. Your graph might look like this. Here's A, here's B, and okay, and here's C. Its value is above f of A and f of B. All right, everybody understand that? The y value has to be in between your y values. Therefore, you have that. Okay, so the example they gave you, they told me this is 2, f of 2 is up here at 6. Here's 4. Well, that doesn't make sense. Here's 4. It's down here at negative 2. So here comes my graph. All right. Show that a 0 between 2 and 4. Well, here's 0. Its x value has to be between 2 and 4 because 0 is between 2 and 6. And what you have to write is, given, it's long and complicated, f of 2 equals 6 and f of 4 equals negative 2 and 0 is between negative 2 and 6, the IVT theorem applies, and therefore there exists a C such that 2 is less than C is less than 4, where f of C is equal to 0. Okay, that's all I got. When you apply the IVT, you have to show that the conditions exist, that it's continuous, and that your y value is in between the y values. Stay tuned. I'm going to make a separate video of some examples. Bye.